Welcome to another deep dive. Today we're going to explore something pretty wild, uh, scaling deep learning models. You know those AI systems that just keep getting bigger and smarter?
Oh, yeah. It's amazing how much they've grown recently. We're typing models with billions, even trillions of parameters.
It's insane, right?
Yeah.
And all those parameters need a ton of computing power to train.
It's true. Like, imagine trying to bake a massive cake in a tiny toaster oven. It's just not going to happen.
Exactly. And that's where scaling comes in. We've got some cool material here from a recent workshop, actually.
Oh, yeah.
Yeah, by the Ministry of Electronics and Information Technology and Quantify. It breaks down how researchers are handling this whole scaling challenge.
So it's like a behind-the-scenes look at how they train those AI giants.
Exactly. But before we get too deep in the weeds, let's start with the basics. Why are researchers so obsessed with making these models bigger and bigger? Is it just a bigger is better thing?
Well, it's not quite that simple. Larger models usually do perform better, but it's not just about size. It's more about complexity. Bigger models can capture more of the nuances in the data.
Okay, so do me an example.
Sure. Think of a language translation model.
Yeah.
A small one might be able to translate basic phrases, but a larger model with more parameters can understand things like idioms or cultural references and produce much more natural-sounding translations.
So it's not just memorizing words, it's about understanding the meaning behind them. That makes sense. But you mentioned earlier that training these models needs some serious computational power. What are the main challenges there?
Well, one of the biggest hurdles is memory. These models are so huge, they just can't fit into the memory of a single GPU. It's like trying to pour the ocean into a teacup.
Yeah, I see what you mean.
And even if you could squeeze it in, the training time would be crazy long. We could be talking years or even decades on a single GPU.
That's where multi-GPU and multi-node training come in, right? It's like calling in reinforcements to handle a job that's too big for one person.
Exactly. Multi-GPU training uses multiple GPUs on one machine to share the workload.
Well,
Like you're building a giant Lego set with a friend. Each of you has your own bricks and instructions, and you work together to finish it faster.
I get it. And multi-node training uses multiple machines, each with its own GPUs, right? So it's like multiple teams of Lego builders, each working on a different part of the model.
Precisely. Both approaches help us break down the training process into smaller chunks. And that brings us to the concept of parallelization.
Parallelization.
Yeah.
That sounds intimidating. Break it down for me.
All right. Think of it this way. You've got a mountain of laundry to fold. You could do it all yourself, which would take ages, or you could get your family to help. That's data parallelism.
Ah.
You're dividing the laundry across multiple workers, your family.
So each worker gets a different part, and they all work at the same time to get it done faster. What about model parallelism? How's that different?
In model parallelism, you split up the model itself, not the data, like building a car. You wouldn't have one person try to assemble the whole thing alone. You'd have teams for the engine, the body, the electrical system, and so on.
So data parallelism is like having multiple workers do the same task on different pieces of data. Model parallelism is like having specialized workers each doing a different part of a big job.
Yeah, that's a good way to think about it. And without these techniques, we just wouldn't be able to train the huge models that are pushing AI forward today.
It's like constructing a skyscraper. You wouldn't try to do it with just a few people and basic tools. You'd need a massive team, specialized equipment, and a solid plan.
Exactly. And just like in construction, where you have different tools for different tasks, in deep learning, we have different techniques for different parallelization approaches. One of the most important is PyTorch distributed.
PyTorch distributed. That rings a bell? Didn't we touch on that in a previous deep dive about distributed training?
You're right, we did. PyTorch Distributed is a powerful framework that helps us manage the tricky parts of communication and synchronization in multi-GPU or multi-node setups.
So it's like the conductor of an orchestra making sure everything's in harmony.
A great analogy. It provides a set of tools and APIs that make distributed training much easier to handle. It takes care of things like dividing up the data and the model, sending them to the different workers, and making sure they all stay in sync.
Okay, so we have our hardware with multiple GPUs or nodes. We've picked a parallelization strategy, and PyTorch distributed is keeping everything organized. But how do we actually implement all this? How do we tell PyTorch what to do and where to send things?
That's where things get a little more technical, but I'll try to keep it simple.
Sounds good.
PyTorch Distributed has different backends for different approaches.
Backends, like what?
Well, for data parallelism, the most popular one is Distributed Data Parallel, or DDP for short. It's basically a plug-and-play solution for data parallelism. You wrap your model with DDP, and it handles all the hard work, like distributing the data and syncing up the gradients across the workers.
So DDP is like autopilot for data parallelism. We just set it and forget it.
Pretty much. It makes things a lot easier. And for model parallelism, PyTorch Distributed has the RPC framework, which stands for Remote Procedure Call.
RPC. Okay, I've heard of it, but remind me what it is again.
Imagine you have a complex machine with different parts that need to work together. RPC is like a communication system that lets these parts talk to each other, even if they're not physically in the same place.
So like a walkie-talkie system connecting the different parts of the machine so they can coordinate.
That's a good way to put it. In model parallelism, we split the model across multiple GPUs or nodes, with each part doing a specific calculation. RPC lets them communicate and exchange information as needed.
Got it. Each part has its own job, and RPC acts as the communication channel to make sure everything runs smoothly. But with all those messages going back and forth, doesn't it get messy? How does PyTorch keep track of it all?
That's where C10 steps in, our behind-the-scenes traffic controller. This library handles the details of message passing between GPUs and nodes, making sure everything runs efficiently.
C10D,
Yeah.
the unsung hero of distributed training. It's like air traffic control, preventing collisions and keeping those messages flowing.
Exactly. C10D uses a set of optimized tools specifically for deep learning, ensuring that those messages are delivered quickly and reliably, even in massive distributed environments.
Okay, so we've got DDP for data parallelism, RPC for model parallelism, and C10D keeping the communication lines clear. But what about performance? How do we make sure our setup is running as efficiently as possible?
That's an important question. There are a few key things to think about when it comes to optimization. First, we need to choose the right parallelization strategy. Data parallelism works well for smaller models, while model parallelism is crucial for those massive models that can't fit on a single GPU.
And sometimes we might even need to combine both approaches, right?
Exactly. We call that hybrid parallelism. It can be really effective, but it also adds complexity, so it's a trade-off. Another key thing is communication efficiency. We want to minimize the amount of data that needs to be transferred between GPUs or nodes because communication can really slow things down.
It's like trying to choreograph a dance where the dancers are constantly running back and forth across a giant stage. That's going to slow the whole thing down.
That's a great analogy. We need to be smart about how we distribute the workload and structure our communication patterns. And luckily, PyTorch provides us with the tools to help with this.
So PyTorch is like a choreographer who understands how to make efficient movements and spacing on the stage.
Yeah, that's one way to put it.
Okay, cool.
And there are other performance optimization tips we can talk about too. One technique that can really boost things is overlapping computation and communication.
Overlapping, what does that mean?
Think of it like baking a cake. While the cake is in the oven, you wouldn't just stand around. You'd start preparing the frosting or cleaning up the kitchen.
Oh, right. It's all about multitasking, making the most of the time you have.
Exactly. So in distributed training, while one GPU is busy doing calculations, we can have another GPU prefetching the next batch of data or sending gradients to other nodes.
But we keep all the GPUs busy and minimize any downtime.
Right. It's like a well-choreographed dance where everyone is constantly moving, transitioning seamlessly from one step to the next with no wasted time. PyTorch provides tools like CUDA streams and asynchronous operations to help us implement this kind of fine-grained optimization.
Okay, so we've covered a lot of ground here, from the reasons behind scaling to the different types of parallelization, the key parts of PyTorch distributed, and even some practical optimization techniques. It's pretty clear that training these large AI models is not a simple task.
It's challenging, but also very rewarding. And as we explore further, we'll see even more innovative techniques that are pushing the boundaries of what's possible with AI.
Well, I'm definitely ready for more. In the next part, we'll take a closer look at PyTorch distributed, how it manages all the communication and synchronization. We'll also dive into some more practical tips for optimizing performance in a distributed setting.
Sounds good.
Perfect.
So stay tuned. We've got a lot more to explore in this exciting world of scaling deep learning models.
Awesome. Can't wait.
Welcome back to our deep dive on scaling those massive deep learning models. Last time we were talking about PyTorch distributed and how it keeps everything in sync, like a conductor making sure all the instruments are playing together.
Right, like preventing the violins from drowning out the cellos in a giant orchestra. So let's zoom in a bit. What are the key parts of this PyTorch distributed? And how do they actually help us manage all the communication and synchronization that's going on?
Well, one of the most important pieces is distributed data parallel, usually called DDP. That's the workhorse behind data parallelism in PyTorch.
DDP, the data parallelism champ. Okay, remind me again, What is data parallelism, and why is it so important for training these large-scale models?
Imagine you're teaching a big group of students a new dance routine. Instead of one instructor trying to manage everyone at once, you could split them into smaller groups, each with their own instructor. That's basically what data parallelism does. We split up the data across multiple GPUs or nodes, and each device gets a full copy of the model.
Okay, so it's like having multiple dance studios, each with its own teacher, and a group of students all learning the same routine. Got it. But how does DDP make sure this whole distributed dance class runs smoothly?
DDP is like the head choreographer, making sure all the instructors are in sync. It automatically divides the data into batches, sends those batches to the different GPUs or nodes, and then the really crucial part is it synchronizes the gradients during training.
Gradients, right. Those are like the feedback each student gets on their performance, helping them improve. So DDP is making sure that feedback from each studio is shared and incorporated so everyone improves together.
Exactly. And the best part is that DDP does all this behind the scenes. You don't need to write complex code to handle the communication or synchronization. It just takes care of it.
It's like having a magic choreographer who makes sure everyone learns and improves together. That's awesome. But what about when our dance routine is so complicated that we need more than just multiple instructors? What if we need to break down the routine itself?
That's when we turn to model parallelism in the RPC framework. RPC stands for Remote Procedure Call.
RPC, okay, that rings a bell. But can you remind me what that is again?
Sure. Imagine you have a really complex machine with lots of different parts that need to work together perfectly. RPC is like a communication system that allows those different parts to talk to each other, even if they're not physically in the same place.
So it's like a walkie-talkie system that connects different parts of the machine so they can coordinate what they're doing.
Exactly. In model parallelism, we take the model itself and split it across multiple GPUs or nodes. Each part handles a specific calculation, and RPC lets them talk to each other, passing data and gradients back and forth as needed.
So it's like each part of the machine has its own specialized task, and RPC is the communication channel that ensures they all work together smoothly. That makes sense. But with all those messages flying around, doesn't that get chaotic? How does PyTorch keep track of everything and make sure it doesn't become a mess?
Well, that's where C10D comes in. You can think of it as our traffic controller behind the scenes. This library handles all the nitty-gritty details of how messages are passed between GPUs and nodes, making sure everything runs smoothly and efficiently.
C10, the unsung hero of distributed training, keeping all the communication flowing. So it's like the air traffic control system, preventing any collisions and making sure those messages get delivered.
Yeah, that's a great way to think about it. C10 provides a set of highly optimized tools designed specifically for the demands of deep learning, ensuring those messages are delivered quickly and reliably, even in those really complex distributed environments we've been talking about.
Okay, so we've got DDP handling data parallelism, RPC for model parallelism, and C10D keeping all the communication lines clear. But let's talk about performance now. How do we ensure our distributed training setup is running as efficiently as possible?
That's a great question, and there are a few key things to consider when we're trying to optimize things. First, we need to pick the right parallelization strategy. Data parallelism is good for smaller models, but for those massive models that just can't fit on one GPU, model parallelism is a must.
Right. And sometimes we might even need to use both approaches together, right? Like having both specialized teams and multiple dance studios in our dance routine analogy.
That's right. We call that hybrid parallelism, and it can be super effective, but it also makes things more complex, so it's a trade-off. Another important thing is communication efficiency. We want to keep the amount of data moving between GPUs or nodes to a minimum because all that communication can slow things down significantly.
Makes sense. It's like trying to choreograph a dance where the dancers are constantly running across a huge stage. That's going to make the whole routine a lot slower.
Exactly. So we need to be clever about how we divide up the work and how we structure those communication patterns. Luckily, PyTorch gives us the tools to do this.
So PyTorch is like a choreographer who understands the importance of efficient movement and spacing on the stage. What are some other tips we can use to improve performance?
One technique that can really boost performance is called overlapping computation and communication. It's like when you're baking a cake. While the cake is in the oven, you wouldn't just stand around doing nothing. You'd start getting the frosting ready or maybe clean up the kitchen.
Right. It's all about multitasking, making the most of the time you have available.
Exactly. So while one GPU is busy crunching numbers, we can have another GPU prefetching the next batch of data or sending gradients to other nodes. That way, we're keeping all the GPUs busy and minimizing downtime.
So it's like having a really well-choreographed dance routine, where the dancers are constantly moving, transitioning smoothly between steps with no time wasted standing around.
That's a great analogy, and PyTorch provides tools like CUDA streams and asynchronous operations that let us do this kind of fine-grained optimization.
This is amazing. It's incredible how much complexity there is in training these large-scale models,
Yeah.
but it's also really inspiring to see how researchers are constantly pushing the limits of what's possible with AI.
It's a field that's constantly evolving, with new techniques and tools emerging all the time. But the fundamental ideas of parallelization, communication, and synchronization are always going to be crucial.
It sounds like we've covered a lot of ground here. We've gone from the big picture reasons why we need to scale deep learning to the nuts and bolts of multi-GPU and multi-node training, and we've even gotten into some hands-on performance optimization techniques.
We have, but there's always more to explore.
Oh, I bet.
In the next part, we're going to shift our focus and look at some real-world applications. We'll see how these scaling techniques are actually being used to solve challenging problems in fields like natural language processing, computer vision, and even drug discovery.
I'm excited to see how all this comes together in practice. I'm sure our listeners are too. So stay tuned for the final part of our deep dive, where we'll explore the amazing world of real-world AI applications.
All right, welcome back to the final part of our deep dive into scaling deep learning models. We've covered a lot of ground in the last two parts. We talked about why we even need to scale these models, the different ways we can split up the training process.
Right, things like multi-GPU and multi-node training, and how PyTorch distributed helps us manage it all. Exactly.
Yeah.
So it's like we've built this amazing rocket ship, fueled it up, and now it's time to launch it and see what these powerful AI models can actually do out there in the real world.
I like the analogy.
So give me some examples. Where are people actually using these scaling techniques to tackle some of those really tough AI problems?
One of the most exciting areas is natural language processing, or NLP. You remember those large language models we talked about, like GPT-3?
Oh yeah, GPT-3, the one that can write poems and code, and even seems to understand human language better than some people I know.
Exactly. Well, those models are trained on massive data sets of text using multi-node clusters. We're talking about hundreds or even thousands of GPUs working together.
Wow, that's a lot of GPUs.
Yeah, it takes a lot of power to train a model like that. But because of all that training, they can do some incredible things, like writing different kinds of creative text formats, translating languages with amazing accuracy, and even answering your questions in a way that actually makes sense.
It's pretty mind-blowing. It's like having a super intelligent assistant that can help you with all sorts of tasks.
Exactly. But it also means we have to be really careful about how we develop and use these models. Because as AI gets more powerful, we need to make sure it's used responsibly.
That's a good point. We definitely don't want AI to become something we can't control.
Right. And that's something researchers are thinking about a lot these days as they work on scaling these models.
Okay, so NLP is one big area where multi-node training is making a difference. What are some other examples?
Well, another exciting field is computer vision. Researchers are now using these techniques to create models that can analyze medical images, like X-rays or scans, with incredible accuracy.
Wow, that's amazing. So it's like having an AI doctor that can help diagnose diseases.
Yeah, it has the potential to revolutionize healthcare. We're talking about earlier and more accurate diagnosis, which could really save lives.
That's incredible. What about other areas of science? Is scaling playing a role there too?
Oh, absolutely. In drug discovery, multi-node training is speeding up the process of finding new drug candidates. By training models on huge datasets of molecular structures and biological information, researchers can now predict how effective a potential drug might be.
So it's like using AI to accelerate scientific discoveries, potentially leading to breakthroughs in medicine and other fields.
Exactly. But of course, there are also challenges in setting up and managing these massive training clusters. It's not as easy as just plugging in a bunch of GPUs and hit and go.
I can imagine. What are some of the biggest hurdles?
Well, the scale of the infrastructure is one thing. Managing thousands of GPUs across many nodes requires specialized expertise and really sophisticated software. It's like running a huge data center, but on an even larger scale.
So it's a pretty specialized field.
Yeah. And then there's the issue of communication overhead. As we talked about before, all that communication between nodes can really slow things down if we're not careful.
Right, like traffic jams on the data highway.
Exactly. So we need to be really smart about how we optimize both the code and the network infrastructure to make sure the data can flow quickly and efficiently.
So it's a complex and demanding task, but the potential rewards are huge. From breakthroughs in healthcare to faster scientific discoveries, the possibilities seem almost endless.
It really is an exciting time to be working in this field, and it's important to remember that we're still just scratching the surface of what's possible with scaling deep learning. As computing power keeps getting better, we're going to see even more incredible breakthroughs in AI.
It's pretty amazing to think about. But before we wrap up, I want to bring up something we talked about a bit earlier,
hmm
the ethical side of things. These AI models are getting more and more powerful, and we have to make sure they're used responsibly.
That's a really crucial point. As AI continues to evolve, it's our responsibility to ensure it's used ethically and for the benefit of everyone. We need to prioritize things like fairness, transparency, and accountability in how these technologies are developed and used.
Absolutely. So for our listeners who are now fascinated by this whole world of scaling deep learning, what are some of the key takeaways they should remember?
Well, first, remember that scaling isn't just about having a lot of powerful hardware. It's about understanding the principles behind parallelization, communication, and synchronization, and using the right tools and techniques to optimize performance.
Okay, so it's not just about brute force, it's about being smart and strategic in how we approach the problem.
Exactly. And don't be afraid to experiment and try different approaches. There's no one-size-fits-all solution. The best way to scale will depend on the specific model you're working with, the data you have, and the resources you have available.
So it's all about finding the right combination of tools and techniques for your particular situation.
Right. And maybe most importantly, never forget about the ethical implications. AI has the potential to do so much good in the world, but we need to be mindful of how it's used and make sure it aligns with our values as a society.
Those are some really important points to keep in mind. Well, that wraps up our deep dive into scaling deep learning models. It's been a fascinating journey exploring the cutting edge of AI and all the possibilities it holds.
Thanks for joining us on this deep dive. We hope you've gained a better understanding of this amazing field and all the exciting things happening in it.
And as always, keep exploring, keep asking questions, and keep diving deep into the world of knowledge.